Hi folks, we're going to take a look at page 208, number 14, and what they do here is they give us a 100 centimeter wire, okay, and they want to cut this and have us bend it so that we create a square and a circle. Okay, and they want us to find two different things. They want us to find the maximum possible total area and the minimum possible total area. Okay, so since I'm going to have to work with the areas and possibly the circumferences here, let me give some names to my sides. So we'll call the side length to the square x, and we'll call the radius of the circle r. Okay, so let's start with what it is we want to try to optimize. So here what we actually want to optimize is the total area. Okay, so the area of the square is just x squared, and then we have to add to that the area of the circle, which is pi r squared. Okay, but as we've seen a few times now, the function which we have to optimize has two variables in it. Okay, so I'm going to make use of the fact that I know the total circumference of these two shapes. Okay, so I know that the circumference of the square, so 4x, plus the circumference of the circle, 2 pi r, have to total 100. Okay, so let's do our substitution. So now I've got to choose whether to isolate the x or the r. I guess I'm more motivated to isolate the x because I don't want to have a pi in the denominator if I don't need to. Okay, so let's isolate x. So we've got 100 minus 2 pi r divided by 4, and this is 25 minus 0.5 pi r. Okay, so now I'm going to input this into my equation. So the area is given by x squared, which now I'm going to replace with this expression. Okay, so 25 minus 0.5 pi r squared plus pi r squared. Okay, so here, let's expand this. Okay, so we're squaring a binomial, so square the first term. So 25 squared is 625 minus 2 times the first and last. Okay, so I have 25 times 0.5 times 2. So that'll just give me 25. Don't forget the pi. Okay, r. And now we've got plus, so 0.5 squared is 0.25. Okay, the pi also has to be squared, pi squared, r squared. Okay, plus pi r squared. Okay, let's just kind of section this off. Didn't realize how long that was going to be. Okay, and now let's bring everything together. Now, since this is an application question and I'm dealing with pi's, I will approximate the answers here. Okay, so let's bring together the r squareds. So what do we have? We've got 0.25 times pi squared. Okay, so 2. Oh, sorry, and then of course we have to add pi. Okay, so I'm just bringing these two terms together. So plus pi. Okay, so 5.61. So we've got 5.61 r squared. Then we've got the minus 25 pi r. So 25 times pi. Okay, 78.54. So 78.54 r, and then plus 625. Okay, so here's my model. Now let's think about constraints on the variable. Okay, so I guess if there's no circle at all, that means the whole wire is used to make a square. Then I guess r, has to be bigger than 0. Okay, and if the whole wire is taken up with the circle, okay, so that means the circumference is 100 centimeters. So let's kind of write this here. If the circumference is 100 centimeters, okay, so 100 equals 2 pi r, that means r would be 100 divided by 2 pi, so 50 over pi. Okay, so that would be the upper bound. Okay, now there's a bit of a question here. Do we include the endpoints? Because the question does say that you should be creating both a square and a circle. So if you need to create both, um, then these would be open intervals, okay? Because then r can never actually be equal to 0. Or do you allow for all of the wire to be taken up by one shape? So there's an argument to be made either way. I checked what the book does, and it assumes that you can have just a circle or just a square. So I'm going to make this, I'm going to include the equal to possibility. Okay, but there is an argument to be made that the way the question is posed, you wouldn't be including the endpoints. Okay, so hopefully you'll notice here that this is actually a pretty simple function. This is just a quadratic function with a positive leading coefficient. So we should see that whatever critical point we find will relate to a minimum. Okay, so that means a maximum will have to be found at the endpoints. Okay, so let's go ahead, take the derivative. So here we've got 2 times 5.61, so that'll be 11.22, I guess, r. Okay, minus 78.54. Okay, so let's now calculate this equaling 0. And so r here for a critical point would be 78.54 divided by 11.22. Okay, so how about we just call that 7? Okay, so our critical point is r equals 7. Now here, since a is quadratic, so notice here I'm not actually going to check the signs because quadratic functions are functions we know very well. We know r equals 7 gives a minimum value. Okay. Not only does it give a minimum value, it gives us an absolute minimum value. So as long as this is in our domain, that'll be our min that we're looking for. Okay, so let's just check. So 50 over pi is about 50 divided by 3, which is definitely greater than 7. Okay, so that means we've actually answered part B. So part B, okay, the minimum area will occur if the radius is equal to 7. Okay, and let's see what they're actually asking for. Just says how would the wire be cut so the total area is a minimum. Okay, so in this case here, you could probably just leave it this way, that it'll be cut at r equals 7. I suppose we probably should give the side length of the square. Okay, so here x would be equal to 100 minus 2 pi. Okay, I'm just using this up here, 2 pi times 7 divided by 4. And so let's calculate that here. So 100 minus 2 times pi times 7 equals, and then divided by 4, and we get 14. Okay? So r equals 7 centimeters and x equals 14 centimeters. Now, it's hard not to notice that the x is exactly twice the radius. Okay? So it looks as though what's going to minimize the area is when the diameter of the circle is exactly equal to the side length. Okay? So essentially, circle can be inscribed right in that square. Okay? So that's an interesting little thing. Now for part A, we know already that the maximum cannot occur at the critical point because we already know, since it's quadratic, that that's going to be a minimum. So we have to check the endpoints. Okay, so the first thing we'll do is we'll check A at 0. So what happens when r is equal to 0? Okay, so this is just going to be equal to 0, so we just have to calculate the second part. Okay, so let's do that here. So we've got 25 minus 0.5 times pi times r, which is 0. Okay, I don't know why I did that. Okay, so 25 and then squared is 625. Okay, so the area at 0 is 625, so did a bit more work than necessary. And let's calculate the area when r is 50 over pi at the other endpoint. Okay, so let's remember these are two endpoints. Okay, so this one here maybe actually does need to be calculated. Okay, so let's calculate the area. I'm going to use this expression here as opposed to that one. Just seems a little easier. So let's start with 25 minus 0.5 times pi times our radius of 50 divided by pi. Okay, equals, so that whole thing is equal to 0. Okay, not surprisingly, I guess, because the whole part is taken by the circle, and so I'm just left with pi r squared. So pi times 50 divided by pi squared is equal to, oh, I just realized here I put 80 instead of 50, so let me try that again. So pi times 50 divided by pi squared, okay, and about 796. Okay, 796. So this is the bigger of the two, so that means the maximum area occurs when only a circle is formed. Okay, so just to recap here, so we set up our model. Okay, we realized that we were working with a closed interval, so we were guaranteed both a maximum and a minimum, and it turned out that the critical point gave us our minimum value, and one of the endpoints gave us our maximum. Okay, so that's it for this one here. Let's see if I can pan out nicely, and there you go. There's the total solution. Okay, that's it for now.